Hello, I'm Mohammad Hossein Namaki, a PhD graduate from Washington State University. Today I'm gonna talk about Vamsa, a system that we have created in Microsoft. Vamsa is an automated provenance tracking system that extracts provenance information from machine learning scripts that are written in Python. Vamsa was developed in GSL Lab of Microsoft in collaboration with Washington State and Case Western Reserve universities. Let's start with a real-world example to see one of Vamsa's applications. In a big corporate such as Microsoft, various teams are working on developing a machine learning-based system. This ranges from data engineers who collect and manage the data and generate a set of features, to data scientists who construct machine learning models, and to production teams who deploy these models and monitor their performance. An engineer from the platform team identified a data corruption issue in one of the columns of a dataset. Now she had to identify the teams that use this data in their data science scripts and notify them on this issue. It is a time-consuming and error-prone process, given that this column might be used by various teams and different software as an input to their ML models. Providing the repository of scripts to Vamsa, it can automatically identify the set of features or labels fed into models and thus can help this data engineer to notify the corresponding teams that use this specific column. For example, in here, Vamsa can find this script as it has used fail count as a feature in training of the model. ML provenance tracking, or in other words, understanding the relationship between ML models and the data used to train them, is a vital requirement for ML teams. This was observed by our survey across 7 big data companies when we have investigated the importance of Vamsa applications. Indeed, 82% of participants believe tracking provenance between data and ML models can be very useful in multiple scenarios. For example, in model debugging, as we have just seen a case for a corrupted column, or for compliance to detect if personally identifiable data used to train an ML model or not. We have found that practitioners spend many hours per week manually to understand what are the provenance relationships. We have defined ML provenance tracking problem as extracting ML-related information from a data science script. The provenance information includes the type of utilized model, the model variable, the data source that was used for training, the set of columns that explicitly was included in feature set, as well as the set of columns that were excluded, and the included column as the label. While discovering those information is useful, this is not an easy task. Obtaining provenance information manually is error-prone and expensive. Python is the most used language in data science. It has dynamic typing and extensive metaprogramming abilities. However, as opposed to SQL, it is not a declarative language, which makes the automated provenance tracking more challenging. Every day, new libraries and frameworks are releasing. Data manipulation occurs in various parts of the scripts. How to detect data sources in the scripts, and how to assert if this data was utilized as training, testing, validation, or visualization. Finally, how to relate various data sources and models to each other. Which data source was used for which model? Which columns for this specific model? This requirement and challenges call for a principled and automated solution. Indeed, a suitable solution should not require any user input or changes to the user code. It should provide support at least for Python, and it should support existing ML libraries and be extendable to accommodate new ones. Considering the problem and mentioned design principles, Vamsa incorporates 3 major components. In here, we briefly discuss what are the responsibility of each component. In the next few slides, we explain the details of each. Vamsa takes as the input a Python script and feeds it to the first component denoted as derivation extractor. Derivation extractor then statically analyzes this script and constructs its corresponding workflow. The workflow serves as the input of next component denoted as ML Analyzer. ML Analyzer is responsible to add semantic information using a knowledge base of ML APIs. The annotated workflow then feeds into the last component denoted as Provenance Tracker, which using the same knowledge base investigates the operations in the annotated workflow that are related to column modification. It actually tries to find out any operation that are modifying the columns. Vamsa can store this information into data catalog such as Apache Atlas for future usage. Next, we discuss these components in detail. To capture provenance information, we first need to understand dependencies among elements of the script. Given the Python script, derivation extractor analyzes it and converts it to a workflow intermediate representation. Looking at this workflow, we can answer questions such as which variables were derived from other variables, what type of libraries and module were used, and what operations were applied to each variable. This workflow has two types of nodes, denoted as variables and operations. Each variable corresponds to a variable in the Python namespace, while each operation changes the state of the program. Invocation of an operation by an optional caller creates a provenance relationship or PR. Indeed, a PR is a quadruple with a sequence of inputs, an optional caller object, the actual operation itself, and a sequence of outputs. In next slide, we'll discuss how derivation extractor generates PRs and connect them to create a workflow. Derivation extractor starts by converting a Python script to its abstract syntax tree representation. It then parses the tree and generates a set of provenance relationships. Finally, derivation extractor connects these provenance relationships together to form a directed graph. By now, we got a workflow and we know what are the dependencies among variables and operations that produce these variables. However, we do not know the role of each variable, such as if they are ML models, features, labels, or training dataset. We also do not know the type of objects. ML Analyzer is responsible to add this information as semantic to this workflow. ML Analyzer consisted of two building blocks: a knowledge base of fine-grained information about ML libraries and APIs, and an algorithm with forward and backward traversals to propagate the extracted information. The knowledge base knows that if a specific API from a specific library and module called, what are the role or type of each of its inputs and its outputs. For example, if fit is called from scikit-learn library, the role of first input is features and the role of the second one is label. This is always true. The outcome of this call is a trained model. Using this knowledge base, a traversal algorithm is responsible to propagate the semantic information to the variables of the workflow. Intuitively, we should start from import statements and libraries. The algorithm uses these variables as the seed set. For each item in this seed, then, it initiates a DFS traversal in forward manner and asks knowledge base on what should be the annotated information for the input and output of each operation. In this path, if a new annotation found for an input variables, it initiates a backward traversal to propagate this information backward and also ask knowledge base if needed. For easier understanding, let's look at an example. For this one, we have chosen a fraction of a script from a Kaggle competition, which was to predict if given a set of features, someone may have heart disease or not. It starts by importing libraries, reading a CSV file, selecting a set of features, and specifying the ground truths. It then splits train and validation datasets, initializes a model, and sends the training data frames to fit the model. This is the workflow that we get from derivation extractor. Starting from an import statement, ML Analyzer traverses forward to send library and module information. At each provenance relationship, it asks knowledge base and annotates the input and outputs of the operation. For example, by asking knowledge base, it finds out the first input of feed is features and the second input of it is labels, and the outcome of it makes a trained model. As inputs of this operation got a new annotation, we need to start a backward traversal to propagate this information backward until there is no API in the knowledge base or the backward DFS was exhausted. The last component, Provenance Tracker, operates on the annotated workflow. It detects a subset of columns in the training data source that was used as features and labels or excluded from feature set. This algorithm iterates on variables annotated as features or labels and look for operations that modify columns such as drop, iLock, lock, delete, or any type of subscripting. These operations were also captured in the knowledge base of APIs, and Provenance Tracker knows if they are adding or eliminating columns from a set. Now we have created Vamsa, we need to also evaluate it from both accuracy and time perspective. We have used two public and large-scale datasets, namely Kaggle that we have downloaded using Kaggle API and notebooks that crawled from GitHub in 2017. Evaluating the accuracy means that, for example, if Vamsa reported a feature set used in the model or excluded from it, is it a correct claim? As this is a novel problem, there is no public benchmark for it. We thus conducted two sets of experiments. First, we manually extracted provenance information for a small subset of scripts, and then compared them with the results we have got from Vamsa. Second, we experimented how often Vamsa can extract and report the provenance information on large corpus for each individual component. We also randomly looked at the cases where Vamsa could not report any results and reported in the paper. And we also evaluated Vamsa's latency. We manually labeled in total 300 scripts that randomly extracted from both datasets. Note that as Vamsa reports different outputs, we can evaluate each one of them separately. For example, on how many cases Vamsa could find the model variable correctly, or on how many cases it could find the training dataset correctly. On the other hand, note that we get two sets of included columns as features and excluded columns. Considering the columns that were actually included or excluded in the script as ground truths, we can compute precision and recall of Vamsa. In here, the precision shows the proportion of discovered included or excluded columns by Vamsa that were truly included or excluded columns in the script too. While recall, on the other hand, shows how many of actual included or excluded columns in the script discovered by Vamsa. Our analysis shows that Vamsa's precision and recall is higher than 90%, which is promising. Note that the reason for not obtaining 100% accuracy is mainly due to Vamsa's currently implementation and does not require any change in Vamsa's design. For example, we have not covered a few Python grammar in derivation extractor, or we have populated our knowledge base manually, which might lag of some of ML APIs. I discuss more about some other cases in the next slide. We also tested to see on how many cases Vamsa reports an ML model, a training dataset, and a feature list for the large-scale datasets. Note that we systematically investigated the correctness of these results in previous experiments. Our analysis indicates even manual, yet minimal, population of knowledge base leads to high coverage on big collection of data science scripts. Let's answer why in 6% of cases, even though we have expected to find an ML model, Vamsa didn't find any. Note that in our dataset cleaning pipeline, we were looking for scripts that had some kind of training or clustering in it. So in terms of a scikit-learn, we looked for the word fit, and as long as the script had that, we kept it. However, when we were testing Vamsa, for some of the script, this fit wasn't used for training, but for feature engineering. In these cases, Vamsa correctly didn't report any model, even though our simple string matching in the data cleaning pipeline passed this script as an ML script with train. We also found that there were some multi-lines comments that our pre-processing couldn't catch those to remove those scripts from the pipeline. Or some scripts, instead of mentioning the name of the module, used an asterisk that denoted for all modules, and thus the derivation extractor couldn't connect the library to the API correctly. In this work, we have introduced the problem of automated ML provenance tracking. We have designed and developed Vamsa and evaluated it on two large corpus of Python scripts. There are many areas for future work to explore in this space. We are still investigating where Vamsa could not report a valid result to improve its implementation. Moreover, we aim to incorporate runtime information if it's available to identify connections between data source and ML models in more complicated cases, especially for cases that are undecidable under a static analysis setting. Also, can we use runtime information to track partitions of a data source were used for training? In here, we just track columns. So basically, can we track rows? Finally, we need to explore ways to automatically populate the knowledge base. Thank you for watching this video. You can find more information in this link.